Okay, so this question comes from the first page of today's worksheet on angular, tangential, and centripetal acceleration. And it reads, Park Bong-tae of South Korea made 14,628 turns of a jump rope in 1 hour. Suppose that the rope's average angular speed was gained from rest during the first turn of the rope. During this time, it had a tangential acceleration of 33 meters per second squared. What was the radius ropes passed? Okay, so essentially we've got a person who is moving a skipping rope in a circular path. Okay, that rope is accelerating, so we can see here that initially the rope was at rest. Okay, so that tells us that our initial speed is going to be equal to 0 radians per second. Okay, and then he accelerates, which means to speed up, okay, at a rate of 33 meters per second squared. And that is our tangential acceleration. Okay, and eventually he reaches a faster speed, okay, which we don't know. But we do have some information that we can use. I'm going to put this information kind of separate. We have some information up here that we can use to figure out what is WF. Okay, and the information we've been given to figure out WS is we've been given theta. Okay, so in that first sentence, it says that in order to calculate his final speed, he's making 14,000 turns in an hour. So we're going to use that information to calculate the fastest speed that he goes. Okay, so in this particular case, he makes 14,628 revolutions, okay, which is just a trip around that circular path. Okay, and the amount of time that it takes him to make those revolutions are 1 hour. Okay, so both of these variables are not in the correct format right now. So the first thing that I'm going to do is turn this into radians by multiplying it by 2 pi r. Okay, and per 1 revolution. Which gives us approximately 91,910.43 radians. Okay, and then down here, hour is not in the correct units either because the scientific or the standard unit for time is seconds. Okay, so I'm going to multiply this by the conversion factor. 3,600 seconds are in 1 hour, which means we have 3,600 seconds as our time. Okay, so now we've got an angular displacement that this rope has traveled and the amount of time that it took that rope to travel that angular displacement, which gives me enough information to calculate the speed. Okay, so speed is equal to angular displacement divided by time, which means the final speed or the average kind of speed that he ends up traveling at is 25.5 radians per second. Okay, now that I've got his final speed, I can go back to the rest of the question. Okay, so suppose the rope's average angular speed was gained from a rest. Okay, so we started with a speed of 0 and accelerated to this speed, and all of that acceleration happened during the first turn of the rope. So now I have another angular displacement for how long it took the acceleration to occur over. And in this particular instance, the length of the acceleration is given in a distance, but it could also be given in a time as well. Okay, but again, I've been told that this acceleration occurs over 1 revolution. Okay, I need to convert that into radians. So I'm going to multiply by 2 pi rads again. Okay, and I'm just going to leave it as 2 pi rads so I can plug that whole number into my formula and not have to worry about decimals. Okay, so we've got starting at 0, accelerating to this. This is the rate of acceleration and it occurs over 2 pi radians, and we are trying to find the radius. Okay, in order to find the radius, okay, the formula that we've been given in terms of acceleration is that tangential acceleration is equal to angular radiation or acceleration times the radius. So if I want to find the radius, I need to know the tangential acceleration, and I need to divide it by the angular acceleration. Okay, I've been given the tangential acceleration here, and I can use all of the changes in speed to find my angular acceleration. Angular acceleration is the one that we're used to calculating. We calculated on the last worksheet as well, using those kinematics formulas like WF minus W0 divided by time. All of those give you angular acceleration. So the first thing I'm going to do is check those kinematics formulas and find one that can find angular acceleration if I've got the displacement, the initial speed, and the final speed. And luckily there is one. Okay, we've got final speed squared is equal to initial speed squared plus 2 times the angular acceleration times theta. Okay, so in this, I'm just trying to calculate my angular acceleration. So I'm going to rearrange that formula to solve for AR. So I start by ending up with the final speed squared minus the initial speed squared is equal to 2 angular acceleration times theta. Okay, and then I'm going to divide both sides by theta to give me that angular acceleration. Okay, when I plug those numbers into my formula, I should get an answer of approximately 51.9 radians per second squared as my acceleration, my angular acceleration. Okay, then I can take my angular acceleration over here, use my tangential acceleration, and plug those together in order to get a radius, which is equal to approximately 0.64 meters. Okay, so the only thing that's a little bit tricky about this question is understanding that these are kind of two separate points of motion. So we have an acceleration where the rope is going from 0 to 25 rads in one turn, okay, which gives it an acceleration rate of 33 meters per second squared. We're going to use that information to find the radius, but before we do that, we need to find that final speed that is reached by using this first sentence, which tells us about the average speed of the rope. The other thing that's slightly tricky is knowing the difference between tangential acceleration and angular acceleration. There are a lot of formulas that you can use to find angular acceleration, but only one that you can use to find tangential acceleration, which is this one here. And if you have the tangential acceleration and the angular acceleration, you can use those together to find the radius.